we're starting today is chapter 1.1. Chapter 1 for this here. Chapter 1 is a little bit different. It's going to be different from the rest of the chapters that we cover. In that, we're going to be covering a lot of different topics all at once. It's kind of weird that chapter 1 for pretty much every single textbook I've ever come across has been a broad range of topics. And they have some central theme here and there, but it's not across the whole chapter. This is the only chapter that's going to do that. The rest of the chapters 2, 3, 4, is all going to be about parabolas, our quadratic equations. We're going to sit on quadratic equations for quite a while. But this one here, we're going to talk about intervals, set notation, sets, subsets. Also in chapter 1, we're going to talk about solving systems of equations. We're going to talk about translations. We're going to talk about matrices. Broad range of stuff. This is the only chapter that does it. Just giving you that warning, yes, that heads up. Now, first thing we're looking at is interval and set notation. That's what the 1.1 is going to be over. Now, the first thing we're going to see and try to figure out is, what is a set? A set is a collection of objects. That's all a set is a collection of objects. Now, for the most part, we're used to a set being a group of numbers or symbols. It does not have to be a group of numbers or symbols. We could talk about a set being a group of book titles. That could be a set. We could names, places. It's just a group of objects. And we use braces around the set. Whatever the object is, we put braces. One to start, one to end to classify this set is contained with these here. Each element, each object is called an element in a set. Each element is separated by commas. Now, sometimes it would seem a little redundant to use commas if we're talking about apples, oranges, avocados. Like, it makes sense that an apple, orange is not the same thing. But it's still useful to put commas. And this is especially true if we talk about numbers, because 1, 2, 3, if we have commas, we know that it's 1, 2, 3. If we don't, we have 123, because those three right next to each other make a different number. The other alternative, we space them out, but if we space them out, it's just going to look like, why did they just put 123 with weird odd spaces between them? We need a way to distinct and make sure that they are separate. A lot of what we do in mathematics, especially geometry, algebra, across all of it, it seems up to this point, you probably had the statement, why does it matter? Why do we need this notation? Why do we need to write it this way? Why is it important? The big thing behind that and why we write it and denote it the way we do is so that I can write it down, I can have it listed, and not have to sit here and kind of help you understand what it is. We do that across the board with everything. User manual, we need it set up and written in such a way that you don't have to have someone there to explain it to you. That's why we have the notation the way it is. Now, with using this in a set, so if I wanted to write 1, 2, 3 as a set, first thing we would do is put a brace. Let's try again. There we go. 1, 2, 3, brace. Brace, we list the elements, brace. That's it. This set is nice because it has 3 elements. And sets that are nice, easily writable, we can list all of them nicely, easily, and it is actually doable. We're going to list them. Not all of them are going to be nice. Now, positive even numbers is technically considered a nice list or a nice set. Or at least I would call it a nice list or nice set. Now, if we're thinking of this, positive even numbers, what would be the first positive even number? 2, okay? So we can put it first, and then what? 4, and then 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Are we going to be actually able to list all these? No, there's too many. There's an infinite number of positive even numbers, yes? Now, I did say a minute ago that this was a nice set, yes? But we're not able to list them all. Do we have a pattern that has emerged at this point? 2, 4, 6, 8. There is a pattern that we have a set, yes? If we have a set and we've been able to establish a pattern, we can use our ... our ellipses to say this pattern that I have defined is going to keep going on infinitely in this direction. That's why in textbooks where they show you an example or something and do the ... it's saying this pattern I've set up, or kind of what we're describing, is going to continue on this way indefinitely. They do this also where it's cool. We're going to 100. I don't want to list them all. We go 12 ... comma 100. It's going to continue in this pattern all the way to 100. So again, even though we can't list them all, this is still nice because we set a pattern and we defined it. Because even if we didn't have positive even numbers, we can look at 2, 4, 6, 8, 10, 12, ... and know we're talking about positive even numbers. They give us a way to describe this set without having to actually describe it or write it in words. Does this make sense? Will every set work this nicely? No. In those cases, we're going to have to actually get more descriptive in what we do. That's where some of our number types come involved. You should probably have heard of different types of numbers. We classify them in different groups. The bottom of this first page on your note sheet is not going to look like it on the slides. I did do it exactly like the slides for a while, but it took up a ton of paper. So I condensed it for y'all on year 1. Because the first main type of numbers, that kind of smaller box on the top right, or top left, sorry, I get them flipped, is natural numbers. Now, a way I think of it kind of has gotten stuck in my head. Natural numbers are naturally the numbers you count on your hands and your feet. 1, 2, 3, 4. It's our counting numbers. Natural numbers are naturally the numbers you count on your hands and your feet. I got that rhyme stuck in my head, and now I can only think of natural numbers that way. But they're just our counting numbers. I don't know if you've heard this across any of your mathematics or any of the math class you've taken up to this point. I will say it. I will stand by it. Mathematicians are lazy. I kid you not. Mathematicians are lazy. They don't want to write natural numbers. If I want to talk about natural numbers in a proof, we're going to talk about it. I don't say natural numbers. I use this symbol. That n with 2 line is denoted in the mathematical world to mean natural numbers. So especially in proofs, if you've ever come across one, and they talk about xen, like this here, you'll see it written here in a bit, or probably tomorrow. They're talking about the natural numbers. When we see this in a proof, this is the natural numbers. So in telling us that x, this variable, is a part of the natural numbers, we're going to use this n to signify natural numbers. If they don't have to write it out, they don't have to write it out. If they can do it simpler, they're going to do it simpler. If something's already been proven, all you got to do is reference it. Yeah, reference his work. He did it. He proved this part, so we're going to move on. Questions on this so far? Yes, sir. Both are the same. Yeah, where you put that second line really doesn't make a difference. You can put it on the outside of the n or the inside. It doesn't normally go on the right line coming up, but it's normally on the left. The other way that they show it is a capital N that's in bold, or kind of some of the fancy text. So natural numbers are our counting numbers, yes? Our next group that we have that add to the natural numbers are the whole numbers. Does anybody see the difference between natural and whole numbers? There's only one thing. 0. So when we talk about whole numbers, we're saying 0 and our natural numbers. All Natural numbers are whole numbers, but not all whole numbers are natural numbers. The main exception is what? 0. 0 is not a natural number. 0 is whole. That's the only difference. And again, mathematicians are lazy. What do we think the symbol for whole numbers is? We're going to use W. They actually don't have one. Because there's not a big difference between natural and whole numbers. They quantify it, they say 0, and our counting numbers are whole numbers. We can say W, but they don't actually give it a symbol. Then the question, why? Because if I'm going to talk about 0 and our natural numbers, 0 and our counting numbers, those positives, I'm actually going to say the non-negative integers. It makes no sense. It's like, we're not going to talk about whole numbers. We're going to say non-negative integers. Or our non-negative real numbers, 0 and above. Now, for us here, we will use, y'all can use a W with 2 lines. That's perfectly fine. I will take that. There are some that use that. But pretty much most proof books and above have no symbol for whole numbers. They just skip straight past it. Because for the most part, it doesn't add a whole lot. It just adds 0. Integers build on top of our whole and natural numbers. Our integers are our positive and negative counting numbers, our additive inverses. Notice that we're slowly building a number line, getting all of our numbers. The symbols for integers is? Exactly, yes, a Z with a line. It is a Z. Now, I have not researched too deeply into why it's a Z, but the 2 main things that I would assume or kind of get at is, 1, I with 2 lines already taken. The other is the fact that when we give stuff symbols or names, we're not doing it necessarily based off English. Because if we discovered something, our native language is English, yes? We're going to use the English alphabet. We're going to use our language to denote it. However, if we were Greek, we would not use English. We would use our native language. We would denote it in the Greek. I mean, that's just logical. We're not just going to say, okay, I'm going to name this and use the German alphabet. It just doesn't make sense. We're going to use our own alphabet. And with a lot of these here, when we translate them into English, we get the English equivalent, which doesn't always line up. Biggest case in point is slope. What's the letter we use for slope? Because y equals mx plus b, m is slope. Slope does not begin with the letter m. It begins with the letter s, yes? I'm guessing at least one of y'all thought, why is it m instead of s? We get it from the Greek. Greek are really that delved into that. We also get our word for change or elevation from their word from montagne. That's where we get mountain, elevation, montagne, m, slope. So it's more from the root than it is actually what it is in our language. Questions about these so far? Well, we've kind of filled in the number line. Now we got numbers between those numbers, yes? And those are our rational numbers. Rational numbers are any number that can be written as a fraction. Luckily, rational numbers gives us a hint at what they are based off the first 4 letters of rational. A ratio. A ratio is comparing 2 things to each other. Fractions. Rational numbers, ratios. So anything that we can rewrite as a fraction. Natural numbers are rational. Because I can write 2 as a fraction. 2 over 1. That's still just 2. It is a ratio. It is a fraction. Because natural numbers, whole numbers, integers are all rational numbers. 1/2 is not a natural number or a whole number or an integer. It's a rational number. It's only rational. I will save you also having to fully think about what a rational number is, because it is a Q with a line. Integers and rational, we gave them some funny symbols. Questions over our number type so far? Now, we do have rational numbers, but we also have irrational numbers. Our irrational number is defined as a number with a non-repeating, non-terminating decimal number. You should know at least one of these 3. Pi, 3.1415926, going on and on and on. It's a non-repeating, non-terminating decimal. The second one on that list, you're most likely never going to come across it, is phi. It, in mathematics, is considered the golden ratio. If you study Greek architecture, sculptures, and get into that side of things, this shows up everywhere, especially in Greek architecture and their sculptures. The sculptures, the buildings, everything is really built and based off of this ratio. And it's kind of a curved shape, spiraling out, getting bigger and bigger. And the last one there is E. E is an irrational number. It's going to be dealing with logarithmic equations, logarithmic functions, exponential growth, exponential decay. It's delving in that there. We will see that in the spring. The symbol for irrational numbers is our I with 2 lines. Yeah, we've had irrational numbers for quite a while. We've known about irrational numbers for actually quite longer than if I remember right, especially our negatives. Y'all have at least talked about the Babylonian Empire in history at some point, which we're talking 1400, 1500 BCE. They had the concept of irrational numbers. That's before the Romans. It is before the Greeks. They've had irrational numbers for quite a while. It is this I with 2 lines. Now, these are not the only irrational numbers. I know last year y'all were having to simplify radicals, square roots, cubed roots. Did all of them come out nicely? No. Any radical that does not reduce completely, like the square root of 2, is an irrational number. It has a non-repeating, non-terminating decimal. Anything that satisfies that is an irrational number. So there's a lot of irrational numbers. There's a lot of spaces between our natural numbers. We're filling those in. Makes sense? Now, if you notice, all of these are contained in a box. A bigger box for all of this, yes? Because there's one more, and it is real numbers. All of these are real numbers. So if we say something's a real number, it is irrational, rational, natural numbers, whole numbers, integers, rational, irrational, all of these are contained within real numbers. So an irrational number is a real number. A natural number is a real number. And the symbol for real number is an R with 2 lines. That's why rational did not get the R, because real numbers already had it. So that there is a YouTube video. If we have time, if we get back to it, I will pull it up. I will add it. That's actually where I got the natural numbers are naturally the numbers you count on your hands and your feet stuck in my head. When I found that video, I was in college. My roommate at the time, I showed him the video. He thought that's cool. For my education classes, that's fine. He did not like that video after a few weeks. I didn't play it to him. I didn't play it a bunch because part of that line is the natural numbers are naturally the numbers you count on your hands and your feet. 1, 2, 3, 4, 5, 6, and so on. And it's this song and goes through. I would just randomly say natural numbers are naturally the numbers you count on your hands and your feet. 1, 2, 3. And he kept finishing 4, 5, 6, and so on. I mean, that's with anything. Someone starts that rhyme, it's almost we have to finish it a lot of the times. He'd finish it and get upset. I did that a lot, so he got tired of it fast. But we feel pretty good with our number types. Yes? Now, it's helpful in that we could say the set of whole numbers less than 10. Since we know what whole numbers are, it gives us a description and idea of what we're talking about. So with the whole set of whole numbers less than 10, if we want to list it as a set, we start with a brace. What would our smallest number be? 0. So we'd say 0, comma. What's our next one? 1, then, and then 3, 4, 5, 6, 7, 8, 9. Since it said less than 10, not less than or equal to, 0 through 9. Order does not matter in sets, unless we specifically are talking about a grouping or an order where, like, this is describing how a group or a certain allotted set are going to be sitting or organized, then order matters. For all the sets we're going to do, order does not matter. So we can order it however we want. Also, it might be nice to put them in numerical order so we don't lose track of a number. For most of this here, not that big a deal. Questions on problem 3. Let's look at number 4. The set of odd whole numbers less than 24. What would our smallest number be? 1. Why not 0? 0 is even, so we have to start at 1. And then 3, 5, what's our next one? 7, almost 9, then 11, then we'd have what? 13 and 15, 17, 19, 21, 23, and that's it. 24 is even, divisible by 2. That's all we have. Now this one's still nice because even though we do have a good number of numbers, it's not too outrageous to actually take a few seconds and just write those out. Still a nice set. Question on utilizing this here. We ready for the next part? We're not going to get into some of the not nicer sets yet. We're going to talk about something called a subset first. A subset is a set that is a part of a larger set. We consider something to be a subset if everything in that set is contained in the other set. Is when all members of a set A are also contained, or also members of set B. Now, before we start really delving into especially numerical number examples, set examples there, let's think of something a little bit different. Is this classroom, is my classroom contained within the high school? Well, yes, every part of this room's in the high school, yes? So that means my classroom is a subset of the high school because every part of this room is contained in the high school. Is the high school a subset of this classroom? No, because I can go down the hall to my wife's room. I will still be in the high school, but I will not be in my classroom. So we cannot say that the high school is a subset of this classroom. Can we say that the high school is a subset of Oklahoma? Every part of this high school is contained in Oklahoma. Can we say that my classroom is a subset of the United States? Yeah, every part of this is contained in the U.S. That's really all a subset is. Let's take it a step further. Can I say that my classroom is a subset of my classroom? Is everything in this room contained within this room? So a set can be a subset of itself. That is perfectly fine. Because a subset is by definition, everything in a set is a subset as long as it's contained in the other set. The other set does not have to be bigger. We're just focused on the elements within that set. So if we look at A and B here, A has the elements 1, 3, 15, 20, and 27. B has the elements 1, 2, 3, 20, 15, 27, 111. Can we say that set A is a subset of set B? Yeah, everything in A is contained in B, yes? I said it once today. I will continue to say it the rest of the semester. Mathematicians are lazy. If I wanted to say that A is a subset of B, I do not write A is a subset of B. We write this little c, this elongated c, that stands for subset. So those three symbols, A is a subset of B. Like I said, mathematicians are lazy. If we can write it simpler, we're going to write it simpler, shorter, sweeter, to the point. So what that says is A is a subset of B. So this here would say that B is a subset of A. Can we say that that is true? No. B has 111, yes? A does not. So we put a line through it. B is not a subset of A because it has stuff outside of it. You could. We normally go left to right. So B is not a subset of A. Yeah. Questions on this here? Same thing is true with this here. Set A contains the elements A, B. B contains elements A, B, C, D. A is still a subset of B. B would not be a subset of A. We good with subsets so far? Okay, let's make some. So we want to writing subsets in set notation. We're just writing them with our braces. Specifically, we're going to write the non-empty sets. Okay? Now, especially with set notation, this here, you do not have to write it, is not an empty set. This is the set containing 0. So we're talking about sets, we're talking about groups of objects. 0 is an object, 0 is a number. We're not talking about nothing, we're saying that it has the number 0 is contained in it. So if I wanted to say an empty set, we have a 0 with a line through it. This here says that we are talking about the empty set. For all the subsets here, we are going to talk about the non-empty sets because the empty sets can get very tedious very quickly. Because this is the set containing the empty set. It's a set containing nothing. Now I have the set containing the set of the empty set. Think about it like with buckets, because if I have an empty bucket, I can put that bucket in a bucket. It's still empty, I just have 2 of them. So it's the set containing the empty set. I've only done it twice, but we can see how this can get out of hand very fast, yes? Because that means I can also have, we can have both. I can keep adding empty sets indefinitely. We can just keep adding infinitum, and there'd still be more. So when we talk about subsets, we talk about the non-empty subsets, because there's many empty subsets to even consider. We're throwing them all out. So we look at the set 4, 5, and I want to list all of its subsets. I will give you one of them, because one of the subsets is the set containing 4. The set, just put the number 4. What would another one be? The set containing 5. There is one more. Yes. The set containing 4, 5. So it is tempting to say 0, but 0 is an actual element. But because 0 is not in the original set 4, 5, we cannot say it is a subset of it. So 4, 5 is going to be either 4, 5, or 4, 5, because a set can be a subset of itself. So it can contain everything. That's it. If we have 2 elements, there's 3 subsets. 4, 5, 4, 5. So thinking of that, how would we do CD? C, D, CD. Questions on this here? Subsets is kind of nice. It's just C, D, C, D. 1, 2, 1, 2. We feel comfortable with these here, yes? All right. As you see on your note sheet, we're going to move it up to 2, 4, 6. Now, I would highly suggest, especially when you start doing these, there will be a few of these on the homework. Let's do them one at a time. Let's do individual sets first. So that would be what? 2, 4, 6. Because this seems kind of redundant, why just start there? Because I think it's nicer to start with just one element. Because what can we do next? 2, 4. Now, for our case in point, and for this here in subsets, 4, 2, 2, 4, 4, 2 are the exact same set. So we could have 2 and 4. We could also have what? 2, 2 and 6. You could also do what? 4 and 6. The order in which we list this does not matter. I always start left to right. So 2, 4, 2, 6. I just do this for my own personal sake so I don't lose one. Or don't lose track of one or miss one. 2, 4, 2, 6, 4, 6. Are there any 2s? Groups of 2 subsets that we could have? No, but we do have 2, 4, 6, yes? The whole thing. And that's it. Now that's kind of interesting because we started out with sets that had 2 elements, yes? Had 3 subsets. I add 1 element. Go from 2 to 3. We jumped from having 3 subsets to having 7. That's a decent jump, yes? Let's see what happens when we add 1 more. Let's go 4. E, F, G, H. Well, you know we'll have E, F, G, H. We'll get the simple one, the nice one out of the way. We'll get the ones. Let's look at our groups of 2. We have what? E, F, yes? We could also have what? E, G. We can also have EH. Well, really, that's all the ones we can have with E, yes? Where can we go next? FG. We don't care about FE because FE and EF are the same. So we have FG. What else? FH. Well, that's all we can do with F and any combination of 2 with F, yes? What do we have next? GH. Do we have any other groups of 2? No, we're pretty much good with groups of 2. Yeah. If I need to slow down or you need me to slow down, tell me. Tell me to pause, tell me to hold up. You will not offend me at all. So we good with our groups of 2? Yes. What can we do next? 3, yes? I'll start with E, F, G. Just the first 3, yes? But we could also have what? E, F, H. So before I'll wrap this up real quick, the next one we can have, because that's everything with E, we can also have F, G, H. And we also have E, F, G, H. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh. Yep. Where am I moving? E, F, G, E, F, H. E, G, and H. I knew I was missing one. We have 15. 15 subsets with 4. I will tell you this, if we go to 5, you get 32. It pretty much, yeah. I think it's 2n plus 1 or something like that.